Good day, dear colleagues. I'm Željana Nikolić from University of Split Faculty of Civil Engineering, Architecture and Geodesy. And today I will present an investigation related to seismic assessment of historical stone masonry buildings typical for the historical city centers along Dalmatian coasts. The investigation is funded by Interreg Italy-Croatia project with 7 partners, including 4 Italian and 3 Croatian partners. Main activities of the project are assessment of floods, meteor, tsunami and seismic risks, assessment of combined flood, seismic and seismic flood meteor tsunami risks, improved early warning system and risk management plan. Croatian test site chosen for application of methodology developed in the project is Kaštel Kambelovac, one of the 7 settlements in the Kaštela city. Main hazards analyzed in the projects are the floods, extreme sea waves, and seismic action. In each of these phenomena, the hazard of the area and vulnerability of the buildings are analyzed to calculate the single risks. The activities result with vulnerability and risk maps for a single hazard. After that, multi-criteria analyses are applied to calculate multi-hazard risk based on individual risks. All results for single and multi-hazards are given in the web map based on Graphical Information Systems tool. The main results are methodologies for vulnerability and risk assessment and vulnerability indexes for buildings, hazard maps, vulnerability maps, and risk maps. Test site Kaštel Kambelovac consists of historical center with stone masonry buildings built between 15th and 19th century and part outside of the center, mainly with masonry buildings built from the half of the 20th century to nowadays. The seismic hazard level for Croatia is defined with 2 maps for return periods of 475 and 95 years, expressed in terms of the peak ground acceleration. In the Kaštela, the seismic hazard for the soil type A is equal to 0.22 G and 0.11 G. According to Eurocode 8, soil factor S for ground type different from A increases the ordinate of the elastic response spectrum. Therefore, our Italian partner OGS performed geophysical investigation along the 3 lines in Kaštel Kambelovac in order to define the soil characteristics. The results of investigation are soil class A for the whole area. Therefore, the constant seismic hazard at the whole test site was assumed. The building in the historical center were constructed with stone blocks with mortar joints and wooden floors. The buildings were constructed without confining elements and with poor connections between the walls and floors. Some buildings are in very poor condition without mortar in the joints, with significant cracks in the walls, and in some cases with collapsed roofs. Several buildings are completely demolished. The first part of the investigation is seismic vulnerability assessment performed by original Italian vulnerability index method. The method was improved with modifications proposed by Tuscany region to consider the substitution of original light timber floors with reinforced concrete slabs. The method can applicate it to all masonry buildings with irregular or regular stone blocks, masonry buildings with concrete or clay blocks, with confinement or without confinement. The method is based on evaluation of 11 parameters and vulnerability indexes normalized in the range between 0 and 100%. Based on the developed methodology, Excel sheet was created and used to compute the vulnerability indexes of the building. The calculation is here shown for Camby Tower protected historical buildings. The calculation results with a vulnerability index for each building. The vulnerability indexes for 75 buildings in the historical core and 35 buildings outside of historical core were calculated. The results are presented in seismic vulnerability map. The buildings were divided into 4 vulnerability classes: low vulnerability, medium low vulnerability, medium to high, and high vulnerability. The distribution of vulnerability shows that the most buildings in the historical core belong to the high and medium to high vulnerability classes. Special distribution of 11 parameters which influence to the vulnerability index is presented here. Vulnerability map for the whole test site is shown in this slide. The map shows highest vulnerability in the historical core with the stone masonry buildings. The buildings in the historical center mostly belong to high and medium to high vulnerability classes, with the vulnerability indexes higher than 45%. The vulnerability index is not a relevant indicator of seismic risk because it does not give information about the behavior of the building under specific seismic action. Therefore, the relation between damage, acceleration, and vulnerability indexes by observing the damage to masonry buildings under real earthquakes was performed by Italian researcher. In this work, instead of field observation of the damage caused by past earthquakes, a non-linear static pushover analysis was performed for the buildings at the test site. And the yield and collapse acceleration for typical buildings were determined. The damage index is expressed in the space between 0 and 1 by a trilinear law defined by 2 points. Yield acceleration represents the damage which is equal to 0, and collapse acceleration which represents the damage which is equal to 1. Non-linear static pushover analyses were performed for 11 buildings in the historical core and 8 buildings typical for the area outside of the historical core. Non-linear static pushover analysis is used to estimate the behavior of the buildings up to the failure, especially yield and collapse acceleration. Thematic software was used. 3D model of masonry structures based on macro elements represents the nonlinear behavior of masonry panels and piers. We analyzed the response of the structure along the 2 orthogonal axes in both positive and negative directions. We also applied accidental eccentricity equal to 5% of the maximum floor dimension, and we used in total 36 analyses which represents uniform linear L modal lateral load distribution. Capacities of the structure is expressed in peak ground acceleration corresponding to the end of bilinear curve for collapse state and for the yield point. The seismic capacity is compared with seismic demand for each building, and we also analyzed the local mechanism failure. The analysis is here shown for one of the typical building. This is public library. This building is made of stone blocks in the 19th century. And with wooden floors and roof. This is the photo of the building, plan and section view and the model of the structure. We obtained 36 curves for all analyses, which are represented here, and the worst cases of pushover analysis is presented in this diagram. A validation of critical peak ground acceleration was performed according to N2 method defined in Eurocode 8. For this building, we obtained the collapse acceleration, which is equal to 36% of peak ground acceleration for the period equal to 472.5 years. And we obtained for early damage state peak ground acceleration equal to 22% of the same peak ground acceleration. We also analyzed the local mechanism failures, but in this case we obtained that the critical accelerations are valid for global analysis. Nonlinear static pushover analyses are also performed for several buildings outside of the historical core. So these buildings are made of concrete or clay blocks, confined or unconfined, depending on the building period. And these are the results obtained for typical building periods. We can see that the buildings, unconfined buildings built before 1964 do not satisfy the seismic demand, and contrary to that, buildings built according to modern European seismic regulation satisfy the seismic demand. Yield and collapse peak ground acceleration were obtained for the 11 typical buildings in the historical center and presented in this table. We also developed relationships which connect vulnerability indexes with peak ground acceleration. We obtained two curves, one for the collapse acceleration and one for the damage acceleration. We can use these curves to define the yield and collapse acceleration for other buildings which were not analyzed detailedly as these 11 buildings. We also established relation between vulnerability indexes and capacity acceleration for 19 buildings analyzed with pushover analysis. This relation is important because it can give an approximation of the accelerations corresponding to collapse, significant damage and yield for the building based on their vulnerability indexes. This figure shows the map of collapse acceleration for historical center. We can see that only few buildings satisfy the seismic demand, the blue one, and all other buildings do not satisfy seismic demand. Achieved collapse accelerations of the buildings are mostly below 50% of the demand acceleration. The next step is definition of vulnerability curves for the buildings at the test site. These curves are defined in a way that we calculate the peak ground acceleration, which correspond to the damage equal to 0, and collapse acceleration, which correspond to the damage equal to 1 by pushover analysis, and each building is represented in this diagram with its vulnerability curve. Vulnerability curves are used to define the damage index for the building with known vulnerability index and demand acceleration. This map shows the damage indexes for 95 years, where the demand acceleration is equal to 0.11 G. This figure shows that the buildings in historical center has mainly the damage equal to 1, and buildings outside of the historical center has a low value of the damage. The most buildings in the historical center has damage equal to 1 for the return period equal to 225 years. And finally, map of damage index for return periods 475 years shows that the buildings in the whole test site mostly have got index of the damage equal to 1. We also analyzed the risk maps for 3 return periods, where the risk is shown by a risk indicator, which is the ratio between the capacity P ground acceleration and demand ground acceleration resulting from the studies of seismic hazard. This map shows that for return periods equal to 95 years, the few buildings in historical center are non-safe because their risk indicator is lower than 1. For return periods equal to 225 years, almost all buildings in historical center are non-safe. And finally, for the maps equal and return periods equal to 475 years, all buildings in historical center and a lot of buildings outside of the historical center are non-safe. And finally, I will emphasize some conclusion. The methodology for seismic vulnerability assessment of historical city center is presented here. The methodology has been applied in Kaštel Kambelovac, one of the 7 settlements of Kaštela city, with a typical configuration and buildings that are representative of other small and medium historical centers in Dalmatia. The approach combines the calculation of vulnerability index and numerical investigations of typical buildings with nonlinear pushover analysis. A new damage vulnerability P ground acceleration relations have been developed using vulnerability indexes and the yield and collapse acceleration of the buildings obtained through pushover analysis. The derived vulnerability curves allow us to estimate the damage to buildings in the unit of specific seismic action. Vulnerability and risk of the buildings in the area are represented with several maps, vulnerability index maps, critical P ground acceleration maps, damage index maps, and risk maps for 3 different return periods. The methodology can be applied to and calibrated with other historical settlements. Thank you for your attention.